Thank you. So I want to more or less pick up where I left off in the morning, kind of thinking about what structure we get on the image of the circle in an extended three-dimensional TFT. And more generally, the question we're asking is, we're thinking about these functors, obviously. Let's call it Z. And we're sort of asking what structure does Z of S1 have, or said differently, what structure does it need to have? So what I mean by that is sort of two questions at once. On the one hand, if we were given such a functor, what do we see as the structure on the resulting linear category? And on the other hand, if we were trying to build such a functor, what structure do we need to give to a linear category to be able to build it? And they're really, the answers are the same to both questions, which is why I'm not being so careful to distinguish them. And so the answer so far is that Z of S1 is a braided tensor category. Okay, and so then the plan now is two parts. So we need to see what remaining structure we have, and there's just one piece of structure left. So Z of S1 has what's called a twist, which is sometimes called, there's a condition on the twist, which is sometimes referred to as it being compatible with the braiding, or sometimes referred to as it giving a balanced twist or giving a balanced category. And then that's going to be all the structure, and then we're going to look for properties of this braided tensor category with a twist. And they're going to be three properties, namely that Z of S1 has duals, that is, objects have duals, and is what's called a ribbon category and satisfies a condition called modularity that squeaked into Andre's talk. So let's get started thinking about the twist. Well, suppose we're given such a functor now. Then we can think about the following transformation. So if we have the cylinder, there's the Dane twist automorphism of the cylinder, which I'm going to convey like this. So I'm drawing this red line on the surface of the cylinder, and I'm going to draw the image of the red line under this diffeomorphism. So it squeaks around the back and then goes back up the front. So that's the right-handed Dane twist. Let me call that theta. And so this goes to some, so both of these are the identity transformation. So I have the category C, so C is Z of S1. And on the one hand, I have the identity, that's this functor. And on the other hand, I have the identity, that's this functor. And then I have a three-manifold between them. So recall that theta is really a three-manifold, the way I'm thinking about it, because this is, I'm really always thinking about the mapping cylinder of this diffeomorphism. So diffeomorphisms of surfaces you should think of as three-manifolds. So they're giving two morphisms in the target category. So this is giving some map, which I'll also call theta, which is a natural transformation of the identity functor of C. So what does that mean? So this is a natural transformation. So then for each object A of C, what do we have to do? Well, both the source and target take that to A, and we have to give a map, an isomorphism between them, which I'll denote theta sub A. So this is some automorphism of every object of C that's natural. And so this is called the twist on A. Okay. And just sort of to compare notation, so recall we had the braiding was also a natural transformation, and we might have denoted, I don't recall if I used this notation, but we might have referred to the braiding on objects A and B being some transformation, some natural automorphism from the product one way to the product the other way. Okay, and so the question now is, how is this piece of data related to the stuff we've already constructed? So that's really the compatibility between theta and beta. Well, in fact, we already did the computation this morning. We saw that if we took beta squared, it was an automorphism of the product, and we saw that that was equal to the thing where we did theta on each of the incoming legs and theta inverse on the outgoing leg. And so that just directly translates into an equation on this natural transformation theta in the target, namely that beta of BA, beta of AB should be equal to theta of AB inverse times theta of A times theta of B. Okay. So for some unknown reason, I've called this equation star star in my notes. Okay, so that's condition one, but that turns out that's not the only relation we have. There's one more, which is how theta interacts with the unit in our category, the unit of the multiplication. So we can also think about compatibility of the unit and the twist theta. So I guess I've started turning my boardisms on the side. I think I'm going to schizophrenically turn them back and forth, so just bear with me. So if I have theta here, so there's theta, and then if I cap it off by a unit on the incoming boundary piece, well, these two, this diffeomorphism just unwinds, and so this is now isotopic to, this diffeomorphism is now isotopic to the identity, and so I can write this as the identity on the unit piece, and then theta on that piece is just equal to the identity. And so that implies the equation that theta on the unit object, so this transformation, this cup transformation, takes C as a vector space to the unit object, which I called 1 of the category C. So this is the unit object of the category C, and that should just be equal to the identity automorphism of that unit object. And so I'll call this equation star. Okay, and so that's all we need. So now we can define a braided tensor category with a twist satisfying both of these two equations is called a balanced tensor category. So now we know that the image of that our fusion category associated to any three-dimensional field theory is in fact a balanced tensor category. Okay, so now as we've been doing, we ask the question, well, what kind of algebra would we need to produce this kind of structure in its representation theory? And so we ask about balanced structures on Hopf algebras. So that's the next section. And so just to write down what I just said aloud, we're asking what structure do I need on some braided, I guess we've been calling it A, some braided Hopf algebra A comma R, such that A mod is balanced. Well, this is by now a familiar procedure, but I find it entertaining, so let's do it again. So what do we need? Well, we have A mod, and we are looking for an endomorphism, an automorphism of the identity functor on A mod. So we're looking for something like this. So again, what does that mean? Well, it means that for each M, we need to give some automorphism of M, theta. And so we ask, well, how are we going to produce an automorphism of M? Well, here, more or less, the first thing you might guess is the right answer. So we're just going to take an element M and multiply it by some element, which I'm going to call nu. So here, nu is some element of A that we can just act on this module by. Well, and we want this, we want this to be, the Dane twist is invertible, so this had better be a natural isomorphism, so this had better be an automorphism, so nu had better be an invertible element of A. And so now we need to know when it is that we actually constructed an A module map. So let's check that. So is this an A module map? Well, if we start with M, then on the one hand, we can multiply by some element of the algebra, and then we can do, oh, sorry, I just turned things on the side. So I'm thinking I'm going to check if theta going horizontally from M to M is a module map. So that takes M to nu times M. And then if I act by A, that goes to A nu M. But if I act by A and then take the twist, then I get nu AM. And so for those two things to be equal, I need that nu is central in A. So we're actually looking for an invertible central element of our algebra. Okay, so so now then, so that ensures that we have a module map, and now we need to ensure these two compatibility conditions. So let's start with the second one, the compatibility with the unit. So let's think about the unit condition. So what we want to know is that the twist on the unit object is the identity. So what's the unit object? Well, the unit object is just the complex numbers as an A module. And so the twist here is, well, sending lambda to nu lambda. But what is, this is nu acting on lambda, but that is, what's the definition of that action? Well, it's via the co-unit of nu. And so for that to be the identity, we need that the co-unit of nu is 1.
We already fixed nu that works for every
No, nu does not depend on m. So, yeah, from naturality. So, yeah. Okay, so now we want to look at the condition on the braiding. Let's see. Yeah, good. Okay, so now what do we need? So basically we just need to compute, both sides of this equation in terms of our modules. So we're now starting with two modules, m and n. And on the one hand, we do the braiding to n tensor m, and then we braid back to m tensor n. So here, m and n are both A modules. So let's compute that. So here we had m tensor n. These are elements. So that goes to the R matrix times n tensor m. And then that, well, I twist both of these around and then multiply by the R matrix again. So this goes to R times R opposite. I've switched the factors. Or let's call it R bar times m tensor n. Okay, and then on the other hand, that's supposed to be equal to this product of twists. So what is that product of twists? Well, on the one hand, I'm supposed to act on I'm supposed to act by the twist on one element and then on the other element and then on the product, but actually the twist doesn't depend on the elements at all. So let me do them one at a time. So I have m and n. So first of all, I can just act by the twist on that factor, and then I can act by the twist on this factor, and then I need to act by the twist on the whole thing, but the twist is just one element, and so the way I act on a tensor is by taking the coproduct. And actually, I needed to do the inverse twist after I'd multiplied them, so this is really new inverse there. So we get another condition, which is that R bar is equal to delta nu inverse of nu tensor nu. Okay, so let me call this 1 and call this 2. And so now, as you can probably guess, we're going to define an invertible central element nu in A, where this is some braided Hopf algebra, is called a balancing element if it satisfies 1 and 2. And so by construction, if you have a braided Hopf algebra with a balancing element, then say it's called A, then A mod is balanced as a tensor category as defined over there. Again, just by construction. Okay. And so it's worth remarking somehow I haven't used, in this whole discussion, I haven't actually used the antipode of the Hopf algebra at all. So, if I were trying to be a little more careful, I would really have said bialgebra here. So bialgebra was the structure I got when I took the definition of a Hopf algebra and just erased everything involving the antipode. But we tend to think about Hopf algebras, and most of the things we work with are Hopf algebras, so tend to refer to that even when we're not using the structure. Okay. So then a note, which is that now if I do want to take into account the antipode, then so you'll recall what did we see? So we saw that the point of the antipode was that it gave A mod duals. It allowed us to construct dual representations. And so once you have dual representations, you can ask how the twist behaves on the dual representation and how that's related to the twist on the existing representation. And so there's some more compatibility conditions if you take that into account. And so if this element nu satisfies further conditions, involving the antipode, then it's called a ribbon element. And so if you actually have a braided Hopf algebra with a ribbon element, then the representation category is a ribbon category, not just a balanced category, as you might imagine. So if you have a ribbon, so if you have a Hopf algebra with a ribbon element, then that implies that your braided tensor category is actually a ribbon category. I realize none of these things have been defined yet, but we will define them all. So you might think we're going to be going and proving this, but in fact, just so you have the lay of the land, it turns out that a Hopf algebra with a ribbon element is the same thing as a Hopf algebra with what's called a charmed element. And it turns out it's easier to prove that a Hopf algebra with a charmed element leads to a ribbon category. And so this is actually what we're going to prove. And this is something Andre is going to do tomorrow. So that's how it's all going to fit together and how we're going to end up with a ribbon category at the end of the day. So where are we? So kind of continuing that overview a little bit. So if we have a three-dimensional extended TFT, then what have we constructed so far? Well, we've constructed a balanced tensor category. And we've also seen that if we started with a braided bialgebra with a balancing element, then we could produce a balanced tensor category. Oh, thank you. I'm abbreviating so much, I'm not sure it matters, but anyway, braided bialgebra with balancing. Okay, and so, but of course, at the same time, we're trying to go the other direction. We want to be able to take a balanced tensor category and actually produce a TFT. And so the surprising claim is that we now have all the structure. So there's no more data required to build a three-dimensional topological field theory than what you've seen so far. You just need a balanced tensor category, okay? now it has to satisfy a bunch of conditions. So to go the other way, we need this balanced tensor category. Sorry, let me draw this a little lower. So now to go the other way, we want to... So we're trying to go this way, and we need it to satisfy a bunch of conditions, so it needs to have duals. And it needs to satisfy compatibility with the antipode, which compatibility with those duals, which is called ribbonness, and then it needs to satisfy a further condition called modularity that we'll talk about tomorrow. And now, so what things on the Hopf algebra side lead to these things? Well, here this was I'm just drawing this again, this was the braided I algebra with the balancing. And so then we saw we've already seen that provided it's Hopf, that we have duals. That was the very beginning of everything. And then I promised you that Andre would show that if it comes with a charmed element, then it's going to lead to ribbon. And so you might imagine that we just do another something here to get modularity, but that's actually not the case. That's not the way it works. Instead, you start with this much, and you build a ribbon category, and then you work at the level of the category, doing some fancy business involving quotienting that category to get to a modular category. So we start with algebra and then move over to representation theory and work there for a while, and then do the topology to continue on. So once you have all that, then we're going to be able to build the whole thing. Okay. Is there a question back there?
Well, I'm wondering, you didn't get the structure of Hopf algebra by that information. So I wonder if you start with such a category and produce your fusion category that does not come from a Hopf algebra, or that at least we do not know how to produce from a Hopf algebra. Can you get a TFT?
Oh, sure.
So that statement is really at the level of category. That you're working with the category, you can prove that you can construct this whole business by assigning that category to S1.
Yeah, definitely. These things, this side and this side are completely separate discussions in that sense.
Okay. It seems to me that proving that you can actually build a whole func for this DFT might be an idea.
Well, you better come back tomorrow then. Okay. So I've claimed that, oh boy. Okay, so I've claimed that we have all the structure we need, which seems kind of bold because lots of basic things are still missing. So for instance, we have the pair of pants and we have the unit, but we haven't even talked about the pair of pants going the other direction. So we don't even have all the two-dimensional structure yet. So let's at least deal with that. So the rest of the 2D structure. So again, I'm now kind of, well, yeah, no, that's fine. So what's the deal here? So given A and B, so I'm now going to make a general statement that's going to help me understand the rest of the 2D structure. So given two linear categories that are both semi-simple and have finitely many simple objects, lots of things are much better behaved. So in particular, then any functor, call it f, from A to B, has both a left and a right adjoint, and those adjoints are actually equivalent. So that situation is called having an ambidextrous adjoint. So this has an ambidextrous adjoint. We've been using the words dual and adjoint interchangeably, so I hope that's not confusing anyone. So what does this mean? This means some morphism, which I'll denote F dagger, which I'm not dual because I'm no longer distinguishing left and right, because it works as both. So from B to A, it functions as both a left and right adjoint. Okay, so I can just tell you what that functor is. So, namely, so if I write F as a map from vect to the K to vect to the L. So we had this little side discussion yesterday where we noted that any linear category satisfying these conditions is really just a sum of copies of the category of vector spaces, one for each simple object. And so what does a functor from a bunch of copies of vect to a bunch of copies of vect look like? Well, if I decategorified and replaced vect by C, it's just a matrix. It's just a K by L matrix. And here, so it's just a matrix of vector spaces. So this, I can encode this by a matrix Fij, where each Fij is itself a vector space. And then, if I've written things that way, then the ij entry of the adjoint functor is Fji star. So that is, I take the transpose of this matrix of vector spaces, and then I take the dual of each individual vector space. And I guess I'll leave it to you to think about the fact that that does actually provide a left and a right adjoint to such a functor. Okay, so now that was all sort of an abstract aside, so now we want to build the rest of the 2D structure. Well, so what do we have? So we certainly know what the pair of pants is. That's our product on our category, and we know the unit on our category. And well, this is some functor from C tensor C to C. And so that, well, it gives, there exists some adjoint functor necessarily, and that's the candidate functor for the, so that's going to be the candidate for Z of the pants going the other way. So let me say what I mean by candidate. What I mean is, well, if I'm given a TFT, then that definitely will be the value of the copants, because the pants and the copants are ambidextrously adjoint in the Bordism category, and so that structure just maps into an ambidextrous adjunction in linear categories, and so that's pinned down as this functor. But what I mean really is that the other way, if I'm starting with a tensor category and I'm trying to build a TFT, then I know what the product is, and I take its adjoint, and then I define this to be that adjoint. And similarly, then Z of the adjoint of Z of the unit is our candidate for Z of the cap operation. Yeah?
In the Frobenius case, you can use the co-evaluation or the other way around to go from one to the other, right? And there is no analog here?
Well, no, it's not so different. I mean, so a different way. So, at a very big distance, what I just said is the product determines the coproduct. And what you said is essentially the same thing. You said there's a way to get from the one thing to the other. So more specifically, the same relations here hold up to natural isomorphism. So you could tell the same story a different way, which would be take the coproduct. You somehow need to pin down what this map is if you want to say it that way. So then you say what this map is, and then you have a pairing. Then you have a pairing like this, and then you check that pairing is non-degenerate, and that forces the existence. By then, the same Frobenius argument, that forces the existence of this map. So.
It is one side.
Exactly. Yeah. Okay. So that's the end of the two-dimensional structure. So now, so that was kind of an aside. Now I want to, now just to confuse things, I want to sort of move back up to this part of the story and think, suppose I'm given a TFT, I've built a balanced tensor category, I'd now like to see that it has duals and has a ribbon structure to kind of justify, well, at least to justify the ribbon notion. However, unfortunately, in order to do those computations, I need a piece of technology, which I don't have time to explain today, but I will explain tomorrow. So it's a bit of a break in exposition, but I'm going to ask you to believe some things, and then justification will come tomorrow. So that piece of technology is what are called internal string diagrams, or there's some other name for them in the literature. Maybe they just, I've forgotten what they're called in literature. So this is kind of a preview of something to happen tomorrow. So here's a fact that I will prove tomorrow, which is that suppose I have a surface, say I have this surface, I might be interested in what functor it induces from C to C. Okay? So in particular, to determine that functor, I'm going to denote by I and J and such letters my simple objects. So that functor is certainly determined by what it does to each simple object that I put in at the start. So I have, let me call that surface sigma. So I have z of sigma, and I can apply it to an object I. So this functor is certainly determined by these gadgets. But this is now some element in the category C. And so that element is pinned down by looking at the maps in C from every other simple object J into this object. So this is some vector space. It's some Hopf space in C, which is a vector space because C is a linear category. So this is some vector space. And the fact that those vector spaces encode the functor is something I just invite you to think about. It's maybe seems a little bit confusing at first, but you'll definitely see that that's the case if you think about it. The fact that I'm asking you to believe is that that vector space is the same as the collection of all ways that you can draw string diagrams inside this surface. So, for instance, I could draw some string and put in some vertices where strings separate and come together. Maybe I should have used a different color. I definitely should have used a different color. How about blue? Nope, that looks like white. Can you guys see the difference between blue and white? Barely. No, I don't want to use red because red signifies lines on the surface. And whatever color I'm about to pick specifies lines that are interior to the interior of this thing. Anyway, so that's something living in the three-manifold that sits inside this surface. And such a thing is called, well, one name for it is an internal string diagram. And it should be, so that's inside the surface sigma, and it should be labeled by I on the bottom and by J on the top. So I need to label this top strand J, and all the internal edges need to be labeled as well. So this one might be K, and this one might be L. And whenever I see a vertex, I have a label of that vertex too. So let's say that one's labeled F, and that one's labeled G. And F has to be a morphism from J to the product of the strings that are below it, KL, and then G needs to be a map from, say, KL to I. So that's an example of a kind of string, and what am I allowed to do? This is some gigantic set, so I mod that out by all the different ways of doing an isotopy that doesn't, the isotopy needs to be transverse to the horizontal slices. Like I don't want to introduce any new cups or caps. And then I'm allowed to combine morphisms. So if I had a number of, a couple of different morphisms, I could combine them all together and then use the label that's the composite of those morphisms and split them back apart in some other way. So there are various kinds of operations, and I'll say more about that tomorrow. Yeah?
So it's actually four linear combinations of those values.
Definitely. So Andre's pointing out I really want to be able to combine these, so form linear combinations of all of these guys, and then I certainly need to mod out by some equivalence relation that I've just waved my hands at. Okay. So let me give you some examples that might be clarifying. Or maybe even before the examples, I'll sort of say maybe what the point of introducing this crazy equivalence is, which is that, so if I have some natural transformation, say from Z of sigma to Z of some other two-manifold sigma prime induced by a three-manifold M3, I want some convenient way to describe what this natural transformation is. And so this induces and correspondingly is determined by what it does to these vector spaces. So for simplicity, let me suppose that they both just have one incoming and one outgoing vector space, so then I can just write that they're induced by these maps from Hom J Z of sigma of I to Hom J Z of sigma prime I. So I told you that these vector spaces encode these functors, and the maps, a natural transformation induces a map of these vector spaces, and a map of these vector spaces completely determines a natural transformation. Again, that's not something deep. It's something you just need to think about. Okay, and so therefore, if you believe this fact, it's determined by their effect on these internal string diagrams. And so now, in order to tell you how a three-manifold behaves in this field theory, all I need to do is tell you what it does to string diagrams. And so let me give you some examples of that. Oh, well, okay, I'm going to do this doubly unfortunate thing, and call this an exercise. I'll call this an exercise for tomorrow, which is to say that there's no way you should be able to do it now, but after I do this again in more detail tomorrow, then it'll be an exercise, which is to compute what the braiding is. So here's a picture of the braiding. Okay, so I guess I was drawing the braiding the other way, but so just think about this as beta inverse if you prefer. So to do this now, so to specify this natural transformation, I need to tell you what it does on some string sitting in the middle of this surface with some label f, and that's going to go to this string here. So let me pause and say a little bit about what this means. So again, this is labeled by the same thing, f. So, it's this business is slightly difficult to get your head around because it kind of looks tautological. It kind of looks like we just pulled this leg across here and we just pulled the strings with it. And the notation is designed to make it look tautological, but it's actually not quite, because these things are happening in very different places. Like this, the boardism itself is describing some functor between these different categories, and these strings are describing objects within the category and how they're moving around. And so if I suppose I want to read this green string diagram in this picture, then this line, it starts off, it's going to be labeled by some actual object, J, say, of C. Then I read down, I have some morphism to two other objects, and then I actually braid those two objects in the category, using the braiding of the category. And then you see the category these two strings here, they don't interact, because they're living in different sections of this boardism. So there isn't a second braiding in the category. They just pass through each other, which is sort of it's an ambient symmetric operation between these two big categories. So there you go. So this is how beta acts on these internal string diagrams, and that determines the functor beta. And the other functor we'll need is the twist functor theta. And, well, this one is even more confusing. So I'm starting with an internal string that just runs down the middle, and here I'm just going to act by theta on whatever that object is. So if this object was labeled I, then I just do the operation that's the twist on I in the category. Is there a question up there?
Could you repeat the argument when you were describing, reading the string on the braiding side. So you start with one object, you have a map into the tensor product, but this one is internal now.
Yes.
Is it really just an external tensor product with the other two objects?
Right. No, it's yeah. Well, it's still internal up here, but then it kind of becomes external.
I don't understand how can you possibly do it?
Well, that's the magic of these things. And so it's really a computation. It's not supposed to be obvious. You look at it and sort of maybe you think it's obvious, or better you don't, and then you have to really compute something to see that that it has this effect. And I'll try to say more about that tomorrow, but it's not supposed to be obvious. Yeah.
How many string diagrams you have for a given board is only one?
Well, that's right. That's an excellent point. There usually aren't very many, or, maybe I'm not quite sure what you're asking. So, I mean, so what are you asking before I start drawing random pictures?
I don't understand how you come up with the string diagram. You have to consider all possible strings?
All possible string diagrams. So the claim is that all possible string diagrams are spanning the vector spaces that determine these boardisms.
For a given boardism, how do I know I have all of them, or how do I understand all of them?
What was that?
Theorem is true, we already know the dimension. We already know how to count it.
Well, yeah. Because you are, so part of the equivalence relation that I didn't say very much about is that you're allowed to move things around and compose morphisms. So for instance, suppose I had this surface, I might have something where a bunch of stuff happened up here and then happened over here and so on, and then came together with some more stuff. But I can always push the stuff down by an isotopy. So I can push this down so it's happening more in the bulk.
Okay, I'm not worried about isotopy. I'm okay.
Well, just one more second. See, and then you can just combine all this stuff in the middle into one big morphism. And so then all you're left with, so for, say, this particular surface, every single string diagram has this form with one single label. So you know you have them all. Bit mysterious, isn't it? Yep.
I mean, it seems, I thought at the beginning this theorem that you wrote down there, right, with the fact that the Hopfs are really these formal combinations.
Yep.
So I thought at the beginning that you actually had something that used these two boundaries being the circle, so that you have this map from C to C.
No.
Even if I just don't, I give you now something, a three-manifold without boundary, then I look at this as a map from vec to vec, and I can only label things by C.
Yep.
So I'm looking at the map from C to C, and this should be only one, and I don't see how inside of this three-manifold you can only have one string diagram.
Well, I didn't say you always only have one string diagram. I just said for this particular surface.
In that case, if there's no boundary, you're getting a map from C to C.
Right, which is a numerical invariant. That's the three-manifold invariant. So tomorrow, when we actually compute three-manifold invariants, that's what we're going to do. So you just said that if we had a three-manifold, then that Z of that closed three-manifold is some map from C to C, right?
But I evaluate this at the simple object in vect, and I take this theorem to be true, and I say these are formal linear combinations of all the string diagrams inside.
Exactly.
Oh, I'm sorry. Okay, thanks.
Okay. Okay, so barreling ahead. So let's take that as given for now, and then come back and think about these two here. So the first one. So having duals goes under this other name called, namely, a category is rigid if it has duals. It's just the same terminology. So this is just synonymous to having duals. So the theorem is that Z, so if Z is an extended 1, 2, 3 TFT, then Z of S1 is rigid. So, slight aside, so most of what Andrei and I are talking about is by now quite classical. It's due to Reshtikin and Turayev and Drinfeld and Jimbo and lots of other people. This thing happens to be one more recent contribution to the subject, and there's a nice argument for it due to Jamie Vickery and Bruce Bartlett, which I won't actually present. I just wanted to call that out. So in any case, that means that the category we're talking about really does have duals, which we've seen as a nice property. And so once we know that we have duals, so using that property of rigidity, we can now define or see what the Frobenius-Ader does. So what's the Frobenius-Ader? So what was the Frobenius relation in the two-dimensional case? So in the two-dimensional case, this was actually equal to, well, it's diffeomorphic REL boundary to map like that. So in the three-dimensional case, there's some non-trivial diffeomorphism between these two things, and so there's an induced map from this functor to this functor. And now let me tell you what that map is. Well, actually, I'll just tell you what it does on a very special string diagram, not a general string diagram, since this is the only one I need right now. So suppose, this string diagram is an element of the vector space determining this functor, and it goes to this string diagram here. So what are the labels? This whole string is labeled by I, and so this one's labeled by I, and this one's labeled by I, but this string here is I dual, and so that's why I needed to know that my category itself, C, had duals in order for this to even make sense. And so again, it sort of looks tautological. I just moved the string around, but actually, I have multiple objects labeled by different things in the category, and this here is really a special morphism in the category. It's a co-evaluation map between these two dual objects, and this is, again, some evaluation map between those objects. So I'm actually providing information about these functors by drawing these silly pictures. Okay. So now, with all that in place, we can talk about the ribbon structure. Okay, so let me finally, I've been using the word enough, let me tell you what a ribbon tensor category is. So a balanced tensor category is ribbon if two conditions are satisfied. So on the one hand, if I take some object and I apply the twist to that object, so recall a balanced tensor category is something where I can twist each object, then that should be the same thing as taking the twist on the dual object and then turning the legs around using the evaluation and co-evaluation map. So this is some element I, and then this is I dual, and that's evaluation, co-evaluation. This whole thing is some map in the category C. Okay, I is a simple object of C. Okay, so that's condition 1. Condition 2 is the following. So again, I'm in some braided category with duals, so I can use evaluation and co-evaluation, and I can braid, and I can evaluate and do the same thing. So I can make sense of this as a morphism from an object to itself in C, And that morphism should be equivalent to applying the double twist on C. So these are the conditions that control the compatibility of dual objects with this twist. And then so this is, so far, it's just pure algebra, but now we can see where it's coming from topologically. So the proposition is that Z of S1 is actually ribbon. So what have we seen so far? Well, we've seen it's balanced, and I just told you it had duals over there, so all we have left is to check these two conditions. So let's check the first one. So, you know, the really naive thing to say, well, no, maybe I'll just draw the picture. So suppose I start with the cylinder, then I just do I squunch it up like that, and then at this point I'm going to do a Dane twist along the middle, right there, and then I undo the S curve, okay? So that whole composite is just the same as doing a single Dane twist in the middle of the first cylinder. That's just a geometric fact which you can check for yourself, and it doesn't change the orientation. The right-handed Dane twist here is the same as twisting up and doing a right-handed Dane twist there and untwisting. It's the fact that corkscrews make sense even when you turn them upside down. So that's basically the geometric fact that's leading to this, but you might confuse yourself into thinking it's already a proof, whereas actually you have to do a calculation now using these internal string diagrams. And so we have to actually see what effect this series of functors has inside the category in order to be able to conclude something inside the category. So I start with this morphism in the category, the identity morphism, and I do this operation essentially just involved creating some little legs and then doing a Frobenius transformation. So that now turns into this morphism, again, where this is I dual in the middle. This was I. And then I did the Dane twist, and so I ended up with a Dane twist. This was theta on I dual, so I could have maybe clarified this a bit by saying this was theta I, and this was theta on I dual. And then I undo those twists, and those don't actually affect the string diagram at all, and I'm left with theta on I dual sitting inside like that, and that proves that is the Dane twist, which was the thing that just took it to theta inside. So that's a proof of number one. And now number two is slightly more entertaining. So I'll just do that very quickly and then stop. So number two. So now, oops, wrong color. So now we're going to see a relation in a topological relationship among surfaces that you might not have realized. Like everyone knows this fact about corkscrews, but this is something slightly more elaborate. So we can start by twisting up the surface like this, and then we can do a braiding on this piece here. So braid it around like that. And then we're going to do an inverse Dane twist along that circle there, So that doesn't actually change the surface at all. So, okay, I just moved this leg over a little bit, but that wasn't anything. So that's one transformation that I can do. And here's a different thing I can do. I can instead do the same snake up there, and then do an inverse braiding. So I braid the other direction here. So now I have this surface. So this was Dane inverse, and this was braid. And then I do braid inverse, and then Dane along that same circle, and I get to there. And now I need to compute. And so statement 1, in the geometric bordism category, these two composites are identical. They're the same diffeomorphism. Their cylinders are the same three-manifold. Yes, Raimundo?
The last braiding the last den twist, I think we just exchanging beta with beta inverse.
Say again?
In the last picture, I think you're exchanging beta with beta inverse.
Oh, here? Yeah. So, but the nice thing is that remember that these things in the ambient don't actually mean anything. But yep, it's good to keep track nevertheless. So if I start with a string here, it gets moved to that string there, and then I braid. So what does that do? Well, it comes up here, and then it does an internal braiding in the category, and then comes back down. And then here, I got an inverse Dane twist, so that was theta inverse, and then I had that internal braiding, and then came back down. And on the other hand, I could do this, and then come up here, and then I braided the other way, the other internal braiding, like that, and then I did the Dane twist, so I picked up a theta there, like that, and now I can just look at these two little pieces. If you want to be more precise, you can, to this whole computation, glue on some tails that just undo the corkscrew here, and what you'll be left with is that this morphism in the category is actually equal to this morphism, which hopefully, is not exactly what I wanted to prove, but exercise. That box over there is equivalent to that. Okay, I'll stop there.